scalar triple product. So this particular combination, A dot B cross C, we can calculate if we know the components of each of these three vectors. For example, if the vector A has components A1, A2, A3, and B has components B1, B2, B3, and similarly if C has components C1, C2, and C3, so we can calculate B cross C by following the definition of the cross product. And then we can simply calculate the dot product of these two vectors, which is simply the sum of the products of the corresponding components of the vectors A and B cross C. So in the third step, we just changed a plus sign here to a minus just by reordering these two terms. This expression can simply be put into this determinant. So the scalar triple product can be written in terms of determinant whose first row contains the components of the first vector, the second row contains the components of the second vector, and the third row contains the components of the third vector. A simple formula. Now we note that this scalar triple product can also be written without using the parentheses. We can simply read A dot B cross C. There is no confusion about this notation, since this would have no meaning. Note, A dot B is a scalar and C is a vector. So the cross product of a scalar with a vector is undefined. So A dot B cross C, this expression always means this. Application of scalar triple product. Suppose we have three vectors B, C, and A. The volume of this parallelepiped formed by these three vectors A, B, C with these pink vectors is given by the area of this base and the height. So the area of this base is simply given by, since it's a parallelogram, it's given by the magnitude of the cross product of the vectors B and C. And the height of this parallelepiped is given by the, for example, height over this side over the hypotenuse, the adjacent over the hypotenuse, is the cosine of the angle, which is theta here. So height is simply the magnitude of A times cosine theta. Now we note here that the vector A, the angle between the vectors A and the B cross C could be an acute angle whose measure in between 0 to pi over 2, or could be an obtuse angle whose measure is greater than pi over 2 but smaller than pi. In that case, we would have the value of the cosine negative. So we better put an absolute value symbol here. So the volume of this box is given by the formula as shown here. The area of the base times height, where the area of the base is the magnitude of the vector A cross B, and the height was the product of the magnitude of A times the absolute value of cosine of theta. And we can rearrange these terms, this form, and this can be put into the absolute value of the product of the magnitude of A, magnitude of B cross C, and the cosine theta. But the quantity inside the bars is simply the scalar triple product. So we have the volume as the absolute value, the scalar triple product. So we must be careful in calculating the volume. When we use the formula A dot B cross C, we have a determinant whose first row contains the components of the first vector, the second row contains the components of the second vector, and the third row contains the components of the third vector. We should not be confused ourselves with the bars here and the bars here. These bars are from the determinant, but these bars due to the absolute value. So we better put an absolute value there. So we have the absolute value here. And we have another type of triple product where each of the product is a cross product. So A cross B cross C. So we can simply calculate the B cross C first, and then we can calculate the cross product with A. We also note here the A cross B cross C not same as A cross B cross C. As we know, the cross product is not commutative. So we cannot simply remove the parentheses. This would have no meaning at all.